Alright, this is 5.4, first part of the fundamental theorem of calculus, and I'm just going to go over the concept first, and then we'll hit some of the more challenging problems in the homework assignment. So the idea here, and I'm going to do it the long way first, is let's say I wanted to find dy dx, okay? So I would write this on both sides. I'm taking the derivative with respect to x of both sides, and you'll notice that there's a third variable, t, that's actually inside the integral. And so what I want to prove here is, let's first take the derivative, or the integral of t, and then we're going to plug in our boundaries. So t to the fifth dt is going to go, using the power rule, t to the sixth over 6, and then our bounds are going to be from a to x. We're still taking the derivative with respect to x of both sides, because we're trying to solve for dy dx. Now I can plug in my bounds. And so you see my first bound is x, so I'll end up with x to the sixth over 6. And then I'll subtract when I plug in my lower bound, which is going to be a to the sixth over 6. And by the way, I'd like to say right now that the a I'm using, a is a constant. And that's important that a is a constant for this first part of the fundamental theorem. So dy dx equals d dx of the first component of our integral minus the second component. Now we can use linearity, and we can write this as d dx of the first component of our integral minus the derivative with respect to x of the second component of our integral, and that's going to equal dy dx. Now, the derivative with respect to x of x to the sixth over 6, we could use the power rule, and we'll end up finding that that's equal x to the fifth. And the derivative of this term is actually a constant, because a constant to the sixth power over 6 is nothing but a constant. So this actually goes to 0. And what you'll find is that dy dx equals x to the fifth, which is kind of curious because we look back here and we see that this was t to the fifth. So from this we can extrapolate a tool that will help us when the antiderivative or the integral is not so obvious. And so what that rule states is that, so if I'm looking for dy dx, so in other words, if I'm taking the derivative with respect to x of some function that goes from a to x of t to the fifth dt, or any third variable for that matter, you can actually skip the whole process of integrating and deriving and know that dy dx is automatically x to the fifth. Because we look in here and this is t to the fifth, so we just look at the t and we replace it with an x. And that's what the first part of the fundamental theorem proves, is that the derivative of the integral can be skipped essentially, and what you can do is you can just replace, as long as it's a constant to x, you can just replace the inner function with x to the fifth if you're looking for dy dx. And so that's a kind of a simple way to show why it works, and then in the next problem I'll be working with more of a complicated scenario. Alright, I hope that was helpful, and I'll see you next video.